So this video lets us review Lewis structures that you learned first year, but it's also going to take us beyond those Lewis structures into some more complicated things. And we're also going to learn about formal charge. So a review of the old Lewis dot structure stuff. So remember that the Lewis dot diagrams, you add up the total number of valence electrons for all the atoms in the molecule. Each electron is represented by a dot. You're going to arrange those atoms so that the individual single atoms are going to be paired up to make our bonds. And then you just want to confirm that once you have those bonds drawn, the total number of electrons exactly matches the number of valence electrons you had. So we guarantee that, you also want to guarantee that each atom has an octet of electrons. With the exception of hydrogen and helium, they only need 2. So let's not worry right now about the other exceptions that we come across. And then if you go to Lewis structures themselves, we're going to replace that pair of dots with a solid line that represents our covalent bond. And remember that each line represents one pair of electrons, 2 electrons. But you also have to remember that you still have to show those lone pairs. AP every year has had you do a Lewis structure that I can remember since I've been teaching it. And you've got to be careful to make sure you show those lone pairs of electrons on elements towards the right side of the periodic table, the halogens and so forth. And again, you just want to double check, make sure that everything adds up to the right number of valence electrons. So let's do some practice. So what I'm going to ask you to do is pause it here. Try it and then come back and we will take a look at what you drew. All right, so pause right now and you practice drawing the structures. So we are back at the structure drawing place. So the first one you had to draw was SF2. And so if you remember what you learned first year, sulfur is going to be the central atom. It has 6 valence electrons. So 2 pairs, 2 singles. And then fluorine each has 7. So you're going to put the fluorine so that that lone electron lines up with the lone electron from sulfur. Then you've got that Lewis structure. We're going to change it so that the bond is actually a pair or a line rather than a pair of dots. And so then there's the structure for SF2. If we go on and do the second example, NH3, nitrogen's going to be our central atom. Remember that it's the one that needs the most bonds. So it's got 5 valence electrons. Each hydrogen is going to form a bond to one of those lone electrons on hydrogen. And then there are no lone pairs on hydrogen because they only have that 1 electron. All right, next was the butane. If you remember, 4 carbons is butane. So you had the C's are going to have to be your central atoms. So you're going to have those essentially in a row. Remember, 3-dimensionally it looks a little bit different, but for Lewis structures we can keep them in a row. So we've got the 3 bonds between the 4 carbons, and then the rest of the hydrogens, H3, H2, H2, and H3. So again, we've got no lone pairs of electrons. Everything's involved in bonding. If we continue to go to what was it? CH3O, CH2, CH3. Okay, this is an ether. If I have 1 too many carbons, I forget what the structure was. If I have 1 too many carbons, just take the CH2 out. But you've got C with 4 electrons. Oxygen, remember, has 6. 1, 2, 3, 4, 5, 6. We're going to want 1 bond there, 1 bond to the other carbon. And then the hydrogens will form their bonds. I think it was another carbon, so we'll do this. So single bonds to all of the hydrogens. So there's our Lewis structure. for that guy. And then finally, we had methanol, but I wrote it HOCH3. So again, oxygen 2 pairs and 2 lone electrons, carbon 4 singles. So we're going to have a bond there, and 1 hydrogen to the oxygen and the other 3 hydrogens to the carbon. So you've got those pairs. So hopefully that's what your structures winded up being. All right, so back to the PowerPoint now. So we did those practices, so hopefully you did okay with that. So we covered all single bonds in that last one, so let's take a look at what happens when you have multiple bonds. So remember that you might have to have additional bonds if we don't have enough single bonds to cover everything. So you've got single electrons that remain, or the atoms don't have their octets. Chances are you're going to have double or triple bonds involved. And so once again, we're going to do a couple of examples. So I'm going to have you pause it, try it on your own, and then we'll take a look at the structures together. So CO2, N2, and C2H4. Again, these are just very simple structures. So go ahead and pause it, and when you come back, we'll take a look at the samples. All right, so first one we had was, oh my gosh, I forget, CO2. All right, so CO2, carbon needs the most bonds still, so we're going to put carbon in the center. We're going to put oxygens on the outside. Okay, that's all my bonds. So we know we've got to have 1 bond from each carbon to oxygen, but I've got these lone pairs, and I don't have everything satisfied. I only have 2, 4, 5, 6, 7 around oxygen, 2, 4, 6 around carbon, and 2, 4, 6, 7 around oxygen. So I need more bonds. So I'm going to have that one pair up for a double, that one pair up for a double. So what you wind up with is something like that. It does not matter where you put the electrons, because again, we're doing 2-dimensionals and not 3-dimensional structures. Next one we had N2, oops, just N2, not Ni, just N2. So nitrogen has that 5-electron arrangement, each of them. So we're going to direct the singles towards each other, keep the lone pair away. So 1, 2, 3 is where we're going to have to do the triple bonds. You show them like that, and don't forget Lewis structures require non-bonding electrons to be shown. Last one was C2H4. So once again, the 2 carbons are going to have to bond with each other. So we've got 1 bond there, but I only have 4 hydrogens, and I need a place for 6. So even if I do all of the hydrogens, I'm still short 2 electrons. So I'm going to do another bond there. So again, to show that in a better form, you want to do something like that. All right, so there's multiple bonds. So then let's continue on and continue our conversation about multiple bonds, because sometimes they get a little tricky. Okay. Oh, we already did this one. Okay. So moving on. In other cases, you can't necessarily keep all the original electrons around that atom. You have to be a little flexible. The biggest idea here is that we need to maintain those octets unless you're dealing with hydrogen. So, for example, you've got carbon monoxide and you've got ozone to deal with. Well, the bonding schemes are very weird. So let's take a look at those two. So you don't have to pause, because I think doing this together is a better choice. So let's take a look at what we can do with the carbon monoxide. Okay, so carbon has, oops, can't see it. Carbon has the 4 electrons, oxygen has the 6 electrons. So there's a total of 10 electrons here. Carbon needs 4 more, oxygen needs 2 more. Even if I do this, I don't have anything to pair up with these guys. So you've got to kind of get out of that 6 electrons belong to oxygen, 4 electrons belong to carbon mode, and you've got to be a little more flexible. So what I'm going to need to do is I need another bond here. I need to account for 2 more electrons. So I am going to do a triple bond. That accounts for 6 electrons. Okay, so remember that this was 4 and this was 6. So I need a total of 10 electrons. So there's 6, 7, 8, 9, 10. And if you note, each atom has their octet. 2, 4, 6, 8. 2, 4, 6, 8. So we've satisfied the octet as well as the number of electrons, but this is very weird in terms of what we did first year bonding. The other one was ozone, O3. And you know that if we have 2 oxygens, that's enough to satisfy everybody. Okay, we've got that oxygen double bond going on, and that should make everything happy. Well, where does this 3rd oxygen come in? You're not going to get a ring because that's very unstable. But what will happen is you'll get remember what we called that coordinate covalent bond? You'll get that 3rd oxygen using 1 pair of electrons from that central oxygen, so it'll just keep its own. But if you count numbers of electrons, we've got 2, 4, 6, 8. We've got 2, 4, 6, 8. And we've got 2, 4, 6, 8. So the octets are all satisfied. Ozone, 6 times 3 is 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. Everything's also accounted for there. Sorry, my dots are starting to all blend. I need to make them bigger next time. So it's not quite as straightforward as I forgot to blow that one up. It's not quite as straightforward as you would think. Okay, so, and here's the idea that we need to take a look at then. So in this case, you've got not the normal number of bonds. Sometimes you get the coordinate covalent bond, which is bonds that are where both electrons are donated by the same atom. But remember that the total number of valence electrons can't change, and you have to account for the valence of 8, or the full valence of 8 electrons in each atom with the bonds. All right, so we are running out of time. I'm going to pause it here, and we'll go on to part 2 in the next